All right, in this video, we're going to take our first look at calculus with these polar equations and polar graphs, and specifically focusing just on derivatives here. And as we think about derivatives with polar graphs, we need to keep in mind these conversion formulas that an x coordinate in Cartesian or rectangular graphing is equal to r times cosine theta, and the y coordinate, of course, is equal to r times sine theta. So sometimes we may be asked to find the slope of a polar curve, the slope of the line tangent to the polar curve. And when we are asked to find those things, we are still looking for dy dx, even though our polar curve is, some r equals some function of theta. And so, but slope is still a change in y over change in x, Cartesian rectangular idea. And so what we're going to do here is for dy over dx, we are going to take the derivative of y with respect to theta, because theta is our independent variable for our polar equation. So we're going to take the derivative of y with respect to theta, and we're going to divide by the derivative of x with respect to theta. Because, and we've seen this with parametrics, but let me just remind us that this would be equal to, I'm dividing with fractions, and so I'm going to multiply by this reciprocal, dy over d theta times d theta over dx. My d thetas would divide out, and that does give me dy dx. That's what we're looking for. So let's think about, how do we find dy d theta and how do we find dx d theta? If, we'll start with y. If y is equal to r sine theta, then dy d theta is going to be equal to, now remember that r is a function of theta. It is the dependent variable. Theta is the independent variable for that function. And then sine, of course, here is a function of theta as well. And so what I have going on here is actually a product rule, r times sine theta. So we're going to apply the product rule, which would be r prime times sine theta plus the derivative of sine theta, which would be cosine theta times r. F prime g plus g prime f. And then likewise, if x is equal to r cosine theta, dx d theta, we would also do product rule with r cosine theta. So that's going to be r prime times the derivative of cosine is, oh wait, no, sorry. Just kidding. R prime times cosine theta plus the derivative of cosine is negative sine theta times r. And so when we bring those two things together, dy dx, remember, is going to be dy d theta divided by dx d theta. So r prime sine theta plus, I'm going to switch the order on that second term just because it tends to be a little bit more convenient when you're applying the formula, but you can certainly do it in this order if you choose. And over dx d theta, which is r prime cosine theta minus r sine theta. So this is the polar derivative, the slope of a line tangent to a polar curve. This is what the derivative looks like. If you want to remember this, if you're good at memorizing things and you have room in your brain to memorize that, by all means. I do not have this memorized. I just do the product rule with r sine theta and r cosine theta, because this I know. I know that x is equal to r cosine theta. I know y equals r sine theta. I just do this product rule and come up with the derivative. Okay, so let's look at an example. If we have the polar curve r is equal to 3 cosine theta, and we're going to find dy dx, the slope of the line tangent to the curve, when theta is equal to pi over 2. Now, whenever I'm doing a polar derivative, before I even get into the derivative, I know that I need an r prime, because in our derivative rule, we need r prime as well as r. And so if this is my r, then r prime is going to be the derivative of this, which would just be negative 3 sine theta. That's going to be my r prime. So dy dx. And first thing I'm going to do is write out the rule just so we can have it to reference here. R prime sine theta plus r cosine theta over r prime cosine theta minus r sine theta. That's our derivative rule. So now I'm going to plug in these expressions here for r prime and r in the numerator and the denominator. So my r prime is negative 3 sine theta times sine theta plus r, which is 3 cosine theta times cosine theta, divided by r prime, negative 3 sine theta times cosine theta, minus r, 3 cosine theta times sine theta. That is our derivative. And we are asked to evaluate this derivative at theta equal to pi over 2, which is great. That's an axis angle. This should be very easy. Negative 3 sine of pi over 2 is 1. So I'm just going to go ahead and plug in 1 for both of those sine thetas if theta is pi over 2. Plus 3 times cosine of pi over 2 is 0. Divided by negative 3 sine of pi over 2 is 1. Cosine of pi over 2 is 0. Minus 3 times cosine of pi over 2 is 0. Sine of pi over 2 is 1. And so if I simplify all of this, on the top, I just have negative 3 plus 0. And on the bottom, both of those terms have a 0, and so they become 0. So I've ended up with a dy dx, a slope of a tangent line that is negative 3 over 0, which is, of course, undefined. Therefore, r equal to 3 cosine theta has a vertical tangent line at theta equal to pi over 2. We could also say, I guess I should have started by writing dy dx is undefined. And if we had thought about the graph from the beginning, we could have predicted this. If you remember from our quick look at graphing in the previous video, r equal to 3 cosine theta, this is just going to be a circle centered on the x-axis with a diameter of 3. So that circle, pretend that's round. And so at pi over 2, if I plug pi over 2 into here, cosine of pi over 2 is 0. And so r would be equal to 0 at pi over 2. That's going to correspond to this point. Here we go. This point right here on the graph. And hopefully you can see there that the graph does indeed have a vertical tangent line over there at that point. Okay, we're going to do one more example here. R is equal to 4 times cosine of 5 theta. And we want to find dy dx just in terms of theta. So again, to start out here, I'm going to find that r prime. The derivative here would be equal to negative 4 sine of 5 theta times 5. We got to do a little chain rule on that one. And I'm going to go ahead and simplify that to negative 20 sine 5 theta. I'm going to write out our rule again, and I was wishing last time I had changed colors to do that, so I'm going to change colors this time. dy dx is equal to r prime sine theta plus r cosine theta over r prime cosine theta minus r sine theta. That's our derivative slope of the line tangent to a polar curve. And so for our particular 4 equal to cosine of 5 theta, we're going to plug in these functions. R prime is negative 20 sine of 5 theta times sine of theta plus r, which is 4 cosine of 5 theta times cosine of theta divided by r prime, negative 20 sine of 5 theta times cosine theta plus, not plus, we'll put plus negative. R is 4 cosine 5 theta times sine theta. And in this case, we were just asked to find the derivative in terms of theta, and that's what we have. And so we can stop there. Of course, if we had a value for theta, we could plug it in for all of those and find a numerical slope here. But fortunately, for this example, we don't have to.